Hi everyone, here's a video that's going to go over the notes that we talked about in class for gas behavior, how gases are different from solids and liquids, and what we need to know moving forward, getting into the calculations. So the first one that we started with was defining pressure. We defined it as the collision. So we can define pressure with just one word, and that word is collisions. Anytime these particles hit the sides of the container, they're putting pressure on that, and that's what keeps, say for example, a balloon inflated. Those particles are bouncing all around, pushing on the inside of the balloon. The common units we talked about are kPa, atm, mmHg, and psi. From those, what you really have to know is just recognize them as units of pressure. If the question says a substance is at 13 kPa, you have to know, okay, that's a pressure, so I'm going to plug it into P anytime it's in equation or formula. Next, we move on to temperature. We define temperature as a measurement of the average kinetic energy. Remember, that's the speed. Anytime the temperature increases, those molecules move faster. So instead of saying, oh, that's warm or oh, that's hot, we can actually quantify temperature by measuring that average kinetic energy, that speed. The common units are degrees Celsius and Kelvin. And over here to the side, I just want to make a little side note for Kelvin. So remember that Kelvin is special because it doesn't have any negative values. Absolute zero is 0 Kelvin. And that's when all particle movement stops. All thermal energy is gone, all kinetic energy is gone. But even more, anytime we use temperature in a formula, we have to put that into Kelvin in order to get the correct answer. And oftentimes our temperatures will be given in degrees Celsius. So we have to know how to convert. And that's super easy. It's not like the crazy Fahrenheit Celsius one. All you need to do is take, let's see, so your if I can write here, your temperature in Celsius, and you just add 273, and that equals Kelvin. It's as simple as that. So say your temperature is 0 degrees Celsius, that's 273 Kelvin. So 0 plus 273 is Kelvin. And then to go the other way, you just subtract. So if my Kelvin temperature is 373 Kelvin, then my Celsius temperature would be 100. As long as I added that correctly. I don't really do math in my head. Okay. So one more thing to add here before we move on to volume is we need to make sure that you guys know what STP stands for. So STP represents the conditions at which gases behave exactly like we predict they would. STP stands for standard temperature and pressure. And you do have to know the temperatures and the pressures that qualify as STP, as standard. So for temperature, it's 0. Oops. Come on now. Let me draw. 0 degrees. Oh boy, here we go. 0 degrees Celsius and 273 Kelvin. So that's easy to remember. I'm trying to draw with my finger, so sorry if it's super sloppy. So we have 0 degrees Celsius, 273 Kelvin, and then for pressure, the only ones that you guys need to know is 1 atm or 1 atmosphere and 101.3 kPa. Oops. kPa. There we go. So those are the conditions at which gases behave like they're supposed to. Then we go down to volume. Remember that when we're talking about a gas, we are always referring to the volume of the container that the gas is in. The example that I used in class was, here's this object, say for example, it's my phone. If I hold it in my hand, it takes up space, it has volume. If I set it down on a table, well, it still takes up space, so it still has the same volume. It doesn't change depending on where it's at. However, a gas, if I put it into a little tiny container, it's going to fill up that whole container. All those particles are moving around. If I transfer that gas into a larger container, well, it's still going to take up the whole thing. It's just going to spread out, and it's going to be less dense, and there's going to be less pressure, but it's still the same amount of gas. And so volume is always referring to the container that the gas is in, not the gas itself. Which brings us down to kinetic molecular theory. So here we have KMT, and the 4 main points of this are just discussing how gases move, how gases interact with one another, and how they're so different from how they're so different from solids and liquids. So the first one says that gases are made up of small particles that move in straight lines. So they're moving super duper fast, and they're always going in straight lines. And because they're moving so fast and because they're moving in those straight lines, we can say that the volume of a gas is practically zero or negligible. And that kind of goes along with why we look at the volume of the container as opposed to the gas itself. If we looked at the gas itself, well, the volume would be zero. So, and again, that's because they're moving so fast and they're so spread out. The next two kind of go hand in hand. It says that there's no attractive or repulsive forces, meaning those positive and negative ends that some molecules have won't interact with each other like they do in solids and liquids. And in addition to that, the collisions between particles are completely elastic. So think about a billiard ball. So let's say you have your cue ball here, and then you got your 8 ball over here. Have you guys ever seen where like we hit this ball and the cue ball then stops moving when this one shoots off in the other direction, right? So it transfers the energy. Now eventually this ball slows down. Well, in gases, that's not going to happen. That energy won't be lost to the surroundings because there's no friction, there's no gravity, there's things like that aren't affecting these gas molecules, these particles. So they transfer energy completely, and we're not going to see a net loss of energy. Oops. Okay. So those are the main points of gas behavior, looking at the variables that we're going to be quantifying and the behaviors that gases should have and the conditions in which they'll have it.